the afternoon session. So our first speaker in the afternoon is Antoine Jego. He will talk about height gaps of 2D Brownian motion and the Brownian loops.
Thank you for the introduction and thank you for organizing this conference. So today I'm going to talk about the most basic object we can think of. Brownian motion in the plane, no random environment, nothing. Okay, so one-dimensional would be even more basic, maybe. So this is a 2D Brownian motion, stopped, let's say, after 1 unit of time, for instance. And I will be mostly interested in the behavior of the path in the vicinity of its outer boundary. So here, this is the outer boundary of my path. As we can see, this is a fractal curve. And of course, it has been the interest of many people. There is this famous conjecture of Mandelbrot about the fractal dimension, which has been proved much later by Werner, Werner. And now we know even much more about this curve. So for instance, this is an SLE 8/3 type curve. And the first main result I want to report on today is about the total amount of time my path has spent in a small neighborhood or in a set that is located near the boundary. So I will consider here some set that is really located on an epsilon neighborhood of my outer boundary, and I'm asking myself, what's the amount of time my path has spent there? And the answer is that asymptotically, as the epsilon goes to 0, this is going to be extremely close to 5 over pi times Lebesgue measure. Lebesgue measure of this small open set. So this is a height gap for the occupation measure of the path, because if I were to do the same thing but on the outside of the outer boundary, I would just find 0. So in a way, it means that the occupation measure is constant on the boundary, it's 0 outside, and it is 5 over pi inside. Okay, so that's the first result. Okay, so why is it interesting? So the main, so proving this type of results is difficult simply because the law of the path conditionally on its outermost boundary is neither explicit nor simple in any way. Okay. And so now I want to present the second result, which will not be about only one Brownian trajectory, but it will be about a Brownian loop soup, and it will also explain in a way where this result comes from. What's the broad picture we have behind that. Brownian loop soup. So we have some domain in the plane, and the Brownian loop soup is a soup of Brownian loops. So I'm going to have a bunch of collection of Brownian type loops. They will intersect, of course. They will be a bit everywhere. This is a dense collection, actually, in my domain. And the way it is defined, it's a Poisson point process with intensity given by theta times mu loop. So D is my domain. So here theta is a parameter. And mu loop is a measure, is simply a measure on path. And the way it is defined is as follows. So I will first define it on the whole plane. So I integrate with respect to the duration. So t will be the duration of my loop. Now I integrate with respect to the starting point, the root of the loop, dx. And now I simply have a Brownian bridge measure. So from x to x of duration t. Okay. So this measure is, I mean, if you want, like the factor you have here is extremely natural, because if you want to have a measure that is invariant under translations and invariant under scalings, this is basically the only thing that you can put here. The 4 over pi is a bit more arbitrary, but the 1 over t squared is really the only thing that you can have here. And then in the domain D, the measure is simply defined by a restriction property. So mu loop in D is equal to mu loop in C indicator I stay in D. Right. So this is a natural quantity. And the Brownian loop soup is simply this collection of loops here. In a way, it's maybe not too far from what we have with random interlacements, as Alexis talked about. Instead of having, so before we had a soup of doubly infinite trajectories, now I simply have a soup of loops in dimension 2 here. Okay, and so this is the invariance we had under translation and scaling. Actually, we have much more invariance than that. It's even a conformally invariant quantity, and it turns out to be related to many objects of conformal random geometry. So, and I will mention some of these connections now. So there is a phase transition. So this has been proved by Sheffield and Werner. And the phase transition concerns the clusters of the loop soup. So by definition, a cluster here, so clusters, they are chains of intersecting loops. Okay, so on this picture here, for instance, I have 1, 2, 3, 4, 5. I have 5 clusters, and I have a tiny cluster here that is surrounded by another cluster. And so if theta is not too large, because okay, so this model is increasing with theta. The larger theta, the more loops I have. And if theta is not too large, I have infinitely many clusters. Whereas if theta is at least 1/2, there is a unique dense cluster. So this is more like a subcritical regime. This is a supercritical regime. And moreover, if you are in the subcritical regime, you can look at the outermost boundaries of the outermost clusters. So this is the outermost boundary of an outermost cluster. I'm not considering this one, this tiny one, because it's already surrounded by another cluster. It's not the outermost cluster. And when I look at that, then I have a collection of self-avoiding loops that do not intersect each other. And it turns out that this collection is distributed as a CLE, so CLE kappa. So it's conformal loop ensemble, and this is the loop version of SLE. So this is an important object in this random conformal geometry business. And kappa depends on theta. Kappa belongs to so kappa equals kappa of theta and belongs to 1/3 4. So it's strictly larger than 1/3 because when I send theta to 0, I want to find the same kappa as I had over there, which is exactly 1/3. Okay. So from this perspective, theta equals 1/2 is quite special. It's a critical point, and it's special for another reason. So Legendre isomorphism. So this is a kind of Dinking type isomorphism. If you want, we have mentioned such isomorphism several times already. Here, maybe this is the cleanest isomorphism you can think of, because what it says. So what it says is that the local time of my loop soup. So this has the same distribution as 1/2 the Gaussian free field squared. And that's it. Right, so all the other isomorphisms, usually you have to add something to the local time. You have to say, let me add maybe an independent Gaussian free field, so 1/2 the GFF squared, and then on the right hand side, you will have something which is a bit similar. But here, that's it. In the discrete setting, this identity is really the way I wrote it. In the continuum, it's a bit more complicated. Like both sides of this equation does not make sense actually. So on the right hand side, it's simply because the GFF is a random generalized function, so I cannot a priori square it. So if you want to make sense of this, you need to use a renormalization procedure, and you consider the Vic square of the GFF. And on the left-hand side, you have the same issue actually, the local time. So if I'm interested in the local time of a small, the local time of some region here. So the total amount of time spent by my entire collection of loops. If I simply do that, I find plus infinity, simply because there are too many small loops. So this is not good. And again, you need to subtract. Some infinity here as well. And so there is a Vic type normalization on the left hand side as well. Okay. And again, this particular expression. This identity, it holds only when the density theta is critical, when theta equals 1/2. Okay. So, what do I want to do now? So with Titus and Wei, we wanted to understand what would be the analog, if you want, of this field when theta is not equal to 1/2. And so this is exactly what I'm going to talk about now. So the question, if you want question, what about theta not equal to 1/2? theorem. Okay, so I will be quite vague. There exists a random field. Okay, so actually here I'm considering theta at most 1/2. I need to be in this subcritical regime. We are going to see that I need different clusters. So there exists a random field h theta that depends on theta that is formally given by this formula. Okay, so what do? So I take the local time at x, and I take fractional power, 1 minus theta. When theta equals 1/2, I would take basically the square root. Okay, maybe let me add the 2 if you want. And then I need to add a spin because I want to find a sign field, and so I'm adding a spin where so sigma of C for C cluster, these are IID signs, so plus or minus 1 with probability 1/2, 1/2. And Cx is the cluster containing X. So here I'm considering the loop soup at part of. So here it's very important that the power I have here is so 1 minus theta. The theta is also the loop soup of intensity theta.
What do you mean by the cluster containing X? Which goes through X or surrounds X?
So it turns out that in this expression, X will belong to the closure of a unique cluster, and you consider this cluster. Okay, so maybe this definition is a bit vague. So
but it's not the case that there is a cluster going through every point.
Indeed, it's not the case. But for the points that will matter, it will be the case. Because so okay, let me maybe write one rigorous definition. It would be h theta. I'm summing over all cluster C the spin of my cluster, and then the Minkowski content of my cluster C. So, okay, so what do I do here? I'm first claiming that we are able to make sense of the Minkowski content of clusters. So a sort of uniform measure on the cluster. This is actually far from being trivial.
I'm sorry, I certainly don't remember what the Minkowski content was.
So Minkowski.
I'm the only one probably.
So Minkowski content is so I have a fractal set, or actually any set, and I want to define a notion of uniform measure on this set. So if my set was, for instance, an open set of R2, I could simply consider Lebesgue measure on this set. And another possibility would be to try to consider the Hausdorff measure of this set in a certain gauge function. This would be another possibility. And a third possibility is to consider the Minkowski content of the set. And Minkowski content of the set means that I'm actually considering the epsilon neighborhood of my set. I take Lebesgue measure of this, and then I renormalize this Lebesgue measure. And you need to show that you are able to normalize it, so that when you let epsilon go to 0, you obtain a non-degenerate measure. And this is what you call a Minkowski content. And the gauge measure here depends very much on theta, because the larger theta, the bigger the cluster R, and so it depends on theta.
And where is you? I don't see X in this.
There is no because I mean h theta of x is equal to you. So first of all, it's equal to 0 if you are not on any cluster, and if you are on some cluster, you consider Minkowski content at x. times the spin. And of course, you need to you make sense of this in a generalized way. You don't look at one point, but you integrate against the test function.
This normalization, how do we normalize?
So there is no renormalization in this sum, but there is a renormalization in Minkowski content, of course. And for this one, you use a gauge function that is, so the gauge function is r gives r squared log r to the 1 minus theta plus little of 1. Little of 1 means that there exists some deterministic function. I'm able to use this deterministic function to renormalize my Minkowski content, and it turns out that the way it behaves is like this.
Sorry.
Yes?
The way one should read this is basically the density of the, R squared would be naive if the thing was, say, an open set, and
Yeah.
the log R is basically the density.
And log R is the correction. Yeah. So for the Minkowski content of simply one trajectory, you need to renormalize it using this gauge function where you just take 1 power of log R. And this is, okay, this is quite elementary. And so here, clusters are slightly bigger, but not much. Anyway, so this story is quite complicated, of course, because we are considering very rough objects. So even when theta equals 1/2, this is difficult. I want to take the square root of the GFF squared, but how do I do that? The GFF squared there is a weak normalization, so this thing is not even positive actually. But still, you are trying to take the square root of this thing, and then you need to add signs and so on. And this is quite a long story that started with Titus Lupu on the cable graph, and then recently Aru, Lupu, Sepulveda show that you can indeed do something like that when theta equals 1/2. So really, they were considering the GFF case. And here we are showing that even when theta is not equal to 1/2, you can do something like this. And it's so the main point is really that we are going outside of this Gaussian regime. So theta equals 1/2, things are Gaussian. When theta is strictly smaller than 1/2, we do not have a Gaussian field, and so you need to find ways. And how is it related to? Okay, and in the end, you get a field that is very natural. And so, for instance, the correlations of h theta. This is related to percolative properties, to connection probabilities. Connection probabilities of clusters. So for instance, the 2-point function, the expected value of h theta of x, h theta of y, this would be a renormalized version of the probability that my 2 points, x and y, belong to the same cluster. Okay. So this is one possible definition, and actually our first definition uses even a different technique that relies on multiplicative chaos, so non-Gaussian multiplicative chaos. So we don't have a characterization of this field. If you want, I can tell you that it is not Gaussian. So the fact that it's not Gaussian is quite straightforward, because the local time, this one, it has exponential tails. in the discrete setting, for instance, it's clear. You're looking at the local time at one point. It's an exponential random variable. And if you want to have Gaussian tails, you need to take the square root. And here we're taking a different power. So the tails, they do not match. So why is it related to my height gap story? It's because actually we also have height gaps properties for this field. So constant height gap property for h theta, and this time, so before I was considering the outermost boundary of one Brownian trajectory, and here I'm considering the outermost boundary of the outermost clusters. So across my my CLE kappa loops. So if I go back to this picture, it means that if I'm taking an open set that is located on the epsilon neighborhood of a given CLE kappa loop here, and I'm integrating my field h theta on this open set, I would find that it is asymptotically a certain constant times a Lebesgue measure of this open set. Okay, and when theta equals 1/2, this thing is a celebrated result of okay, so who? Schramm-Sheffield, Miller-Sheffield, and Chian-Werner as well. So here we are talking about really height gap properties of the GFF across SLE4 or CLE4 curves, and so the fact that these curves, they are if you want, level lines of the free field, this has been used level lines of GFF equals SLE4 or CLE4, depending on the context. And in this precise context, it's CLE4. And so if you want, if we go back, this is a very interesting story about the level lines of the GFF. Actually, it has a generalization for any parameter of theta, of my loop soup. So here, okay, maybe it's a bit difficult to appreciate really what's going on because these fields and so on, they are a bit complicated. But in the end, if you send theta to 0, you will in a way go to this picture here. And I'm really talking about a very simple object, which is one Brownian trajectory, and the amount of time it has spent in the vicinity of its outermost. Sorry?
You have to condition, if you send theta to 0, I guess you just get.
So this is
to have one.
So this is more like a heuristic. This is a heuristic picture, and the way we prove this result over there is not by sending theta to 0. We work directly there. I think it would be more complicated to try to use this approach and send theta to 0 rather than working directly over there. So. Oh, I have 1 minute. Okay, in that case, in the remaining minute, I will try to make an advertisement for a paper that should appear on Monday on the archive, which will be about developing a CFT setup for SLE. So what's going on is that SLE, these curves, they describe a scaling limit of critical models, of statistical mechanics models. And mathematicians, they manage to understand very well these critical models in 2D thanks to SLE. But physicists, they have a very different approach to understand that, which is via CFT techniques. And actually, these two approaches, they are currently, there are some links, but they are not that satisfactory. And so what we do in this paper is really to make the bridge between these these two stories, and it has very nice consequences. Okay, thank you.
Any questions?
So, do you have some discrete version of Legendre isomorphism for theta?
So the discrete version would be to say, I do the exact same thing on the cable graph, and the point is to say that when you do that, you could take, when you do that, you can take any power here. But the point is to say, if you take the right power, you don't need to renormalize anything to take to have a meaningful scaling limit. I don't know if it answers your question.
Okay, any more questions?
So I guess you can, another way to think about theta, I guess, is like the dimension of the target. Right, so if you have theta equals 1, then I guess you can get a Legendre isomorphism for like a 2D or a complex JPEG.
Yeah, if you want.
So, is there any way to see that here? Like, is it like what you would expect from a fractional dimensional Gaussian field?
I'm not sure exactly what's your question, because like when theta equals 1/2, I'm just saying you are viewing 1/2 GFF squared plus an independent 1/2 GFF squared. You are saying, oh, this is actually the square of the Euclidean norm of a two-dimensional GFF.
Yeah. But I mean, of
Okay.
course, but I mean, I guess once you get to theta equals 1, then I guess you can have like directed loops and
Yeah.
it sort of seems natural to me.
Mm-hmm. But in a way, you're always going back to theta equals 1/2 when you say that.
Yeah, because you can't count between.
So I'm not sure what I can say about that.
So I guess the other question I have is, on the right-hand side of your equation here, you have the local time, which is something which is well-defined. And then you're saying you define h sort of from this.
Here?
Yeah, I mean,
Right. But
I mean, like, you could have just defined, you could just take any function you want. Like, what's special about choosing this?
So on the right hand side, this is not well defined, because what you want to
Well, after you know, normalizing it correctly, yeah.
right. But so okay. So the point is that if I take a different function here, so here if I normalize it at the level epsilon, and I send epsilon to 0, there is I don't need any renormalization.
So this is
I'm not dividing by anything that diverges or something like that. It's a bit like if you take the discrete GFF and you want to take the scaling limit of this object, you don't renormalize anything. You don't divide by anything. And in the end, you have the continuum GFF.
in
Let's say in 2D, in the domain of 2D. And here it's a bit the same thing if you want. I'm taking an epsilon approximation of this thing, and I take the right power. It's crucial that you take the right power. You don't renormalize at all, and you send epsilon to 0. And then you have this. And if you take a different power, you would need to renormalize, and then the renormalization would kill everything, and you will just have you will have a trivial object in the limit.
I think that's my
Maybe we
but yeah.
postpone the discussion. Yeah, let's thank Antoine again.